So the other major topic that's kind of covered in this chapter is what are the actual three-dimensional shapes of the molecules that we've been looking at. So up until this point in the chapter, you've been looking at how do you draw Lewis structures, how do you know if there's a double bond, how do you know if there's a triple bond, how do you know if there's hypervalency, how do you know if they're electron deficient. And what we're going to look at today is, okay, once you have that Lewis structure, how can you apply it to a three-dimensional space? And for some of you who are very spatial, this is super easy. For others, like me, it's something you really have to work at and really think about. So we know that Lewis structures tell us how they're bonded together, but again, we're not working in a two-dimensional space, we're working in a three-dimensional space. So what we're going to look at with Vsepr is the best approximation of what these guys actually look at. So we know that when we bond, we're using electrons, and again, electrons are negative, so when electrons are near each other, they repel each other. So what they came up with is this lovely thing called Vsepr, called the valence shell electron pair repulsion theory. And basically, it's a way that without building every single model, you can actually predict the shape of different molecules or polyatomics. So what you have here is basically, you use Vsepr when you have more than one thing bonded to the central atom. Like, for example, I'm just going to use, like, dots or something. If I just have two, like, if this is a molecule or an atom and this is an atom, obviously, well, that's a really bad drawing, but obviously, there's just a linear thing, like it is a flat molecule. What we're looking at is when we start adding more things onto this. So, say this crazy squiggle over here is our central atom. What happens when we start adding 3 things to it, 4 things to it, okay? You know, is a flat shape really the best? And that's what we're going to look at. One thing you definitely want to highlight is that unshared pairs of electrons and bonding pairs try to minimize repulsion. So what you're doing is they will find their best situation in the 360-degree world they live in, that they're going to try and be as far away from each other as they possibly can. Just like if you have a mortal enemy and you are sitting near, you're in a class with them, you're going to try and be as far away from them as humanly possible. And another thing that you definitely want to know is that lone pairs actually take up more space. And remember, lone pairs are the ones where they're not involved in a bond. And this slide kind of just shows you this. These are the two different, or some pictures of this one. This is that one if we just have like a dot, and then we just have a bond between them. So that would just be like 2 different ones. But then what we're looking at with Vsepr is, okay, I have 3 things, and they're bonded to a central atom. What's the best way for them to be? And you can use balloons, and they actually do very well. They actually line themselves up into a trigonal planar arrangement. So if you have a central atom and 3 things bonded to it, you actually do get a planar 3-dimensionality thing. When we start doing 4 dimensions, we start getting tetrahedrals. And again, you really need to look at these in your book, and there's a lot of good tutorials online that you should look up because you really have to be able to visualize these 3-dimensionally. So the other thing over here that we just want to show you is that lone pair thing. So we said that lone pairs take up more space than bonded, and that's because they tend to spread out more. And if you look here, we have CH4, NH3, and water. So I'm just giving these to you right now just so you've seen them. But this is the 3-dimensional drawing of methane. And you have your carbon in the middle, and you have 4 hydrogens coming off of it. Just to give you what in the world these like lines and stuff are, regular lines mean that they're in the plane of the paper. Kind of like a colored in triangle means that one's actually coming out of the paper at you. And this dotted line in the back here is actually going away from you. So that's how you draw things 3-dimensionally when you're not really 3-dimensionally drawing them. And if you look at a tetrahedral, or if you look at 4 things coming off a central atom, it's not flat. It is 3-dimensional. And what you find is this angle, well, actually all the angles are 109.5 degrees. That's the best that they can be away from each other. When you introduce ammonia, what you have in here is you still have your central atom, you have 3 bonds, and then you have a lone pair. So what happens here is this lone pair spreads out. It presses down on the bonds a little bit. You can see the little arrows pushing down. And what happens is it compresses the angle. So the 109.5 was the best situation. Well, we add in a lone pair, and now we only have 107. And if you look at water over here, now we have 2 lone pairs. So we're even smaller. And you would expect it would be even more compressed than the ammonia, and it is. It's 104.5. So just keep that in mind. They're all trying to get away from each other, but lone pairs just have this ability to really kind of take over a situation. So what you're going to do is you draw your Lewis structure, and what I've done for the notes is I've already drawn your Lewis structures, because the thought is that you can draw Lewis structures now. And what you're going to do is you're going to count anywhere where there's a high electron density. And what that means is you're either going to count your bonding pairs and your non-bonding pairs or your lone pairs. So you'll actually count those up, and then you'll figure out your electronic geometry and your actual molecular geometry. So an electronic one includes all electrons. So this includes all electrons around central atom. However, molecular only includes the bonding. So a molecular one is kind of like what you would actually see if we could actually look at these molecules in space. The electronic one is kind of what is it based off of. So sometimes these are the same if you have no non-bonding pairs, but a lot of times they're slightly different. So it can be a little different, and that's okay. Alright, so our first one here, I just want to show you, this is beryllium chloride, and this is an electron deficient element, electron deficient molecule, and you can see that beryllium is our electron deficient one, so this is your need, available, and share normally, and what you see is you would need 4 bonds, and that's not going to happen, so I adjusted my need. I end up with only 2 bonds. And then this is my Lewis structure. And again, this is an unusual one. I just wanted to show it to you. This is kind of the classic example of a 2-region one. So what you do is you look at your central atom. So what we care about is anything having to do with beryllium. And what we count is how many bonds there are and how many lone pairs there are just on beryllium. So we have 2 bonds. So I'm going to say 2 bonding areas. And there's no dots on it, so we have 0 non-bonding areas. And that's going to help us figure out what the shape is. So you have this lovely little chart at the end of your notes. And, oh, that's not what I wanted. Let's see if it likes me. What you do is you find bonding domains and non-bonding domains. So you find what you've just figured out. This is not given to you on the AP test. This is not given to you on your test in this class. So these are things you need to learn and understand. And you can see that we have 2 bonding, 0 non-bonding. This is giving us a picture of what it would look like 3-dimensionally. And this is our name. It's a linear molecule. So we come back. Oops. So our electronic shape is linear, and our molecular shape is linear, and that's because we have, there's no non-bonding areas. So the shape that it's based off of and the shape it really is are the same. And they don't always ask you for both, but it's important that you understand that they both exist. What you want to remember is you're looking at just that central atom once you do your Lewis structure. You have to have that first. So we'll do 2 more, take a break, a couple more, and then you're good to go. So next one is boron trifluoride. Remember, fluorine will not form any double bonds. That means boron has to be electron deficient. This is actually one we did back in your notes. So that's what we're looking at here. And again, we're looking at boron once we have our finished guy here. So if we look at this, based on boron, we have 3 bonding areas. We have 0 non-bonding areas. So you go to your chart, and you say, okay, this over here, it tells you the number of electron domains. So just how many total things are we kind of looking at? And we're looking at 3. And we have 3 bonding, 0 non-bonding. So we're based on a trigonal planar. And in this case, we are a trigonal planar. And in fact, this is actually the example of a trigonal planar. So that means our electronic shape is trigonal planar, and molecular shape is trigonal planar. Next one here we have NOCl, and what this one you'd actually have to do formal charges to figure out what way it should go. It ends up that chlorine's a halogen. He does not want to have double bonds on him or anything, so this is where our double bond is. But basically, once you figure out your Lewis structure, you have to find your central atom, which again is nitrogen. And what we need to do is count. Now, one thing you have to be careful of, this double bond still only counts as one bonding area because it's in the same area, it's the same region. So this is a bonding area, and this is a bonding area. So we have 2 bonding areas, and I'm going to just put a little asterisk. Double bond or triple bond counts as one bonding area. And then this time on our central atom we do have a lone pair, so that's what we need to write down. And we have 1 non-bonding area. Again, you need to know what you have before you go to the chart. So you go to your chart and you find that. So I have 2 areas that are bonding, and I have 1 area that's non-bonding. So I'm electronically based on a trigonal planar, but what I'm actually here is bent, and you can see it actually looks bent. And that's what we go back and say. So electronic shape is a trigonal planar, and again, that's if we include the electrons, and our molecular shape is bent.